throw around the word information all the time, don't we? Like, we're scrolling through the news, talking about data. It's everywhere.
It really is.
But like, if you actually stop and think about it.
Yeah.
What is information?
Right.
Like at its core.
Yeah.
Turns out that question has been bugging philosophers for ages.
Oh, yeah.
And that is what we are diving into today.
That's right. So for this deep dive, our trusty guide is the Stanford Encyclopedia of Philosophy entry on information.
Okay.
And let me tell you, it is a seriously thorough piece of work, really mapping out how philosophers have grappled with this concept throughout history.
Good.
And what's really interesting is a dedicated philosophy of information is relatively new.
Oh, okay.
But the seeds of these ideas, they go way back.
I see.
So our mission today,
Yeah.
to trace that philosophical journey, explore those key developments, and unpack the different ways philosophers have tried to understand information.
It's like a history of the idea itself.
It really is.
Okay, so we're kind of like, we're talking about explaining this to someone who thinks really deeply about concepts, a philosopher, I guess.
Right.
Where did this philosophical exploration even begin? You mentioned roots in ancient Greece.
Absolutely. Now, obviously, they weren't using the word information exactly as we do now.
Right.
But thinkers like Aristotle, they laid some really crucial groundwork.
So what were they thinking about that connects?
Think about his concept of form.
Oh, right, form.
For Aristotle, an object's form, that was its essence, what made it that specific thing.
So like what makes it...
Exactly. And you could argue that this form is basically the blueprint, the information that defines it.
So the form, the blueprint, the information all kind of tied together.
Right. And
Wow.
he even used the example, he talked about a 2.1 ratio
Oh, interesting.
to explain certain relationships, kind of hinting at this deep connection between form and underlying principles,
Yeah.
like a mathematical basis.
So the blueprint is the key.
Yeah.
And Plato, with his fascination with numbers, was he also thinking along these lines?
Absolutely. Plato was super influenced by Pythagoras, and he believed that the universe was ultimately governed by this mathematical harmony.
Oh, interesting.
Right. So this idea that reality has an underlying mathematical structure that's like a super early precursor to thinking about information in a quantifiable way.
So if the world can be measured by numbers,
Yeah.
then understanding it involves decoding that
Exactly.
numerical information.
Yeah. It's all about those numbers, man.
Numbers.
Numbers are the key.
Right. And then Aristotle gives us that image, that really vivid image of the signet ring in wax in Diema.
Oh, yeah.
How does that fit in?
That analogy is just brilliant for understanding early ideas about informatio, which is like the Latin root of the word information.
Okay.
So he describes how our senses, they receive these sensible forms of things, but without taking on the actual physical matter. It's like a signet ring, right? It leaves its imprint in wax, but the metal doesn't transfer, just the pattern.
Just the shape.
Right. So the form, the pattern, that's the information. That's what gets transferred.
Okay.
He also compares the mind to a blank writing tablet.
Okay.
A tabula rasa, capable of understanding, but initially empty.
Blank slate.
Totally.
Like you're ready to take on new information.
Yeah, exactly. And these are some powerful early ways of thinking about how we might receive and store information.
Okay. The blank slate idea, I feel like that pops up again and again
It totally does.
in the history of philosophy.
Yeah, for sure. Like thinkers in the Islamic Golden Age, Avicenna, for example, he explicitly developed the tabula rasa concept,
Oh, wow.
comparing the intellect at birth to like pure potentiality, just waiting to be filled through experience.
Okay.
And then you have Ibn Tufayil's philosophical novel, Hayy ibn Yaqdhan. It really explores this idea of a mind developing in isolation, all on its own.
In isolation, so like no outside information.
Just like pure potential encountering the world.
Interesting.
And later on, this work gets translated into Latin, and it has this big influence on John Locke,
Oh, wow.
his version of empiricism and the tabula rasa doctrine.
Okay.
So it's like this through line of thought about how knowledge and by extension, information enters the mind.
Okay, so it's less about what's already there
Yeah.
and more about how we get it.
Yeah, how we come to know.
Okay. You also mentioned the problem of universals.
Right.
How does that relate to a philosopher's understanding of information?
So the problem of universals, it's basically, do abstract concepts like redness or hoarseness, do they actually exist independently of individual red things or horses?
Okay, so it's like, is there a universal red out there?
Yeah, like a platonic ideal of red.
Yeah, or is it just like All the red things.
Exactly. And it gets to this question of how do we categorize and understand the world?
Okay.
Thinkers like William of Ockham, he really wrestled with this, trying to avoid multiplying these abstract entities unnecessarily, you know? And while they weren't using information as their main concept, their debates about universals and particulars, they're essentially about how we recognize patterns, how we see similarities.
Okay.
And that's fundamental to how we process information.
Right, because if you don't have a category,
Right.
it's just like random, meaningless data.
Exactly. It's interesting, though, Aquinas and Scotus, writing before Occam, they were already using informatio and informere in some pretty technical philosophical ways.
Really?
Yeah, in their theological and metaphysical work, which is kind of cool.
Oh, that is cool. So it's like they were getting at something.
Yeah, they were onto something.
Okay, so we've got this groundwork laid in the ancient and medieval periods.
Right.
What shifts when we get to the early modern era?
So the scientific revolution that brought a radical change in how philosophers thought about the natural world, and the Aristotelian framework of four causes.
Four causes, yeah.
That got transformed big time.
Okay.
The final cause, like the purpose of something.
Right.
That was largely set aside for experimental science, you know?
Okay, so more like how does it work rather than what's it for?
Yeah, more mechanical.
Right.
But for our discussion, the really crucial shift was in how they understood the formal cause.
The formal cause.
It went from being this kind of inherent essence to being much more about geometric form in space.
Okay, so like the actual shape, the structure.
Exactly.
And that aligns with the rise of math as like the language of science.
That's it.
Right.
Yeah. So Galileo, for instance, he made this super important distinction between primary qualities, shape, number, motion.
Okay.
Which he saw as like inherent to objects and quantifiable, measurable.
Measurable, right.
Versus secondary qualities, things like color, taste, smell, which he thought were more dependent on our perception. So his focus on these primary qualities that laid the groundwork for so much that came after, including thermodynamics.
Oh, wow.
Which, surprisingly, has some really interesting links to information theory.
Really?
Yeah. So the emphasis shifted towards understanding the world through this measurable, structural information.
So the world is information.
Yeah, okay. Kind of.
All right. And then we've got Descartes. With his focus on ideas.
Right.
How did his thinking contribute?
So for Descartes, an idea that was the very form of a thought, the immediate awareness of our own thinking.
Okay.
He even used inform to describe how these ideas might affect the brain.
Oh, interesting.
But perhaps his most insightful contribution for us is his argument against machines having reason.
Oh, okay.
He basically said that reason is this universal tool, capable of addressing any situation.
Wow.
Whereas a machine, it's limited by its design, its specific purpose. And this has some really big implications for the possibility of AI.
Right, like true artificial intelligence.
Exactly. And it even resonates with the modern concept of a universal Turing machine. Descartes was super skeptical that any machine could truly process information in that general human-like way.
So he draws this line between just mechanical processing.
Yeah, like brute force.
Right,
Yeah,
and something more fundamental to human thought.
Yeah.
Okay, and this sets the stage for the big debate, right?
Oh, yeah.
Between rationalism and empiricism.
Exactly.
Yeah, okay.
So rationalists, following Descartes, they believed in innate ideas.
Right.
Knowledge we're born with.
Okay.
Empiricists, like Locke, they countered and said all knowledge comes from sensory experience.
So it's a blank slate.
Right. And Locke, famously, he reimagined idea as a much simpler, structural placeholder for anything the mind can think about derived from sensation and reflection.
Okay.
So this shift towards experience as the source of ideas. Yeah. That opened the door to thinking about knowledge. Right. And therefore information as something that could be, acquired and built upon, like an additive property, if you will.
Okay, so it's like each piece of information adds.
Yeah, exactly. Builds on what's already there.
Okay.
Yeah.
And around this time, we also see the development of formal probability theory.
Right.
How did that contribute to a philosopher's understanding of information?
So the formalization of probability by thinkers like Pascal, Fermat, and Huygens, that was a major step.
Okay.
Initially, probability was seen as a way to deal with our lack of certainty
Right.
in a world that they thought was deterministic,
So it's like we don't know everything.
Right, exactly.
But the universe is set.
Yeah, like clockwork.
Okay.
But then Hume came along and said, hold on a second.
Okay.
He integrated probability into the very theory of knowledge.
Oh, wow.
He argued that how strongly we believe something should be proportional to the probability of it being true, based on our past experiences,
Okay.
and the possible arrangements of the world.
Okay, so knowledge starts to be seen in terms of degrees of belief.
Exactly.
Measured by probabilities.
Yeah.
A big shift from these, innate structures.
Oh, a big shift. But then along comes Kant.
Right.
And challenges this whole empirical view.
Okay.
He recognized that we have these certain fundamental concepts like space, time, causality that don't seem to be solely from experience,
Okay.
These, what he called a priori intuitions.
A priori.
Right.
Okay.
He argued they're necessary for us to even make sense of our experiences in the first place.
So the groundwork.
Yeah, the framework.
On which we build.
Exactly, yeah. And his whole transcendental philosophy thing that aimed to understand the very conditions that make knowledge possible.
Okay.
Although it didn't directly lead to a formal theory of information,
Okay.
it did influence later thinkers in the foundations of math and logic, which is super relevant for us.
Okay, so it's like he's setting the stage.
He's laying the groundwork.
In a way, yeah.
Yeah.
All right, so we've traced this philosophical groundwork.
Right.
How do we get to the mathematical formalization of information?
Okay.
That's so important today.
Right. So the 19th and 20th centuries saw the rise of all these mathematical tools and theories that directly tackled this concept of information.
Okay.
Now, the development and adoption of positional number systems and logarithms,
right,
while they predate this period,
okay,
they became increasingly significant because logarithms, by turning multiplication into addition,
right,
provided a really natural way to represent quantities that combine additively.
Okay.
Which is this key property we associate with information.
Right. It's like building blocks.
Yeah, exactly.
Of information.
Yeah. And this connects directly to Boltzmann's work on entropy in physics.
Right, Boltzmann.
Yeah, so Boltzmann's famous formula, S called E is K log W, that was huge. And for a philosopher thinking about information, that log W term, that's where the magic is,
Yeah.
It can be interpreted as like a measure of the number of possible microscopic states of a system, which connects directly to our uncertainty about its actual state, or lack of information, you could say.
Okay, so the less information we have, the more possibilities there are.
Exactly. And it links this additive nature of logarithms to the extensive nature of entropy, probability, and crucially, information.
Okay.
Gibbs later refined this.
Okay.
And it was actually his formulation that Shannon famously used.
Okay, so this is building up.
It's all connected, yeah.
To what we use today.
Right.
Okay.
Yeah.
So physics and the concept of entropy, they're providing this mathematical language for thinking about information.
They really are, yeah.
What about a more direct attempt to quantify information itself?
Right.
You mentioned Popper earlier.
Yeah, so even before Shannon came along, Popper was thinking about how to measure the empirical content of a scientific theory.
Okay.
Like how much information it actually tells us about the world. And he realized that a more informative theory, it's also more easily falsified, more easily proven wrong.
Oh, interesting.
Right. So if you have a theory that's very specific, it's easier to find evidence against it.
It's to prove it, yeah.
Exactly, yeah. He even distinguished between what he called logical probability, which is like the inherent probability of a statement being true, and numerical probability, which is more about statistical frequencies.
Okay.
So for Popper, a theory with high empirical content, it actually had low logical probability.
Interesting.
Because it was making very specific claims.
Right, bold claims.
That could be proven wrong.
Okay.
Yeah. And this inverse relationship between informativeness and probability, that's a key precursor to Shannon's work.
Okay.
It really is.
It's like setting the stage. Okay. And that brings us to Shannon. And his groundbreaking information theory.
Yeah.
How did he approach this?
So Shannon, in his seminal 1948 paper,
Yeah.
he was looking to quantify the communication of information.
Okay.
And he came up with this formula for communication entropy.
Right.
It's HP equals negative sum of pi times log base 2 of pi.
Okay.
And it looks super similar to Gibbs' entropy formula, but he applied it to the set of possible messages in a communication system.
Okay.
And using base 2 logarithms, that gives us the measure in bits, which we use all the time today.
Right, right.
But what's so philosophically fascinating is that this formula really captures our intuitive understanding of information.
In what way?
Well, think about it. The amount of information in a specific message, like IX, equals negative log of PX.
Okay.
That aligns perfectly with our intuition.
Okay.
A message that we're certain about, probability 1, it tells us nothing new.
Right. We already know.
Zero information, right? But the less probable a message is, the more informative it is when we actually receive it.
The more surprised we are.
Exactly.
No.
And if we have 2 independent messages, the total information is just the sum of the information in each one.
Okay.
And Shannon actually proved that the negative logarithm is the only function that satisfies these natural requirements.
It's like it's the thing.
It's the thing.
That fits.
It fits perfectly,
Yeah.
So he provides this mathematical framework for understanding information, not in terms of what it means, but in terms of how statistically unexpected it is.
Right. So the meaning is irrelevant.
Yeah, for Shannon at least, yeah.
It's just like how likely was it?
Yeah, how surprising is it?
That we got this message.
Exactly, yeah.
Okay.
That's the key.
It's amazing how he abstracted the idea of information away from its content.
Yeah, he was really focused on that communication aspect.
Right.
Yeah.
But Shannon's approach wasn't the only mathematical approach.
It wasn't, no.
Right.
Right.
What about algorithmic information theory?
So algorithmic information theory, pioneered by Solomonoff, Kolmogorov, Chaitin, they took a completely different approach.
Okay, so what's the difference?
Instead of focusing on those statistical probabilities, they define the information content of a string as the length of the shortest computer program that can generate that string on a universal Turing machine.
Okay, so information is tied to, like, the complexity of its creation.
That's a great way to put it, yeah.
Okay.
So the Kolmogorov complexity, kx, of a string x, it's basically how long is the shortest program that spits out x.
Okay.
You know? And this has profound implications for a philosopher.
Okay. Why is that?
Well, it lets us talk about the information content of individual objects, even single numbers, you know? It gives us a framework for understanding learning as data compression, like finding shorter programs to describe what we observe.
No.
Right. It gives us a definition of randomness. A string is random if the shortest program to generate it is just the string itself.
Oh.
And it even offers a way to measure the predictive power of a theory.
Okay.
A good theory, in this view, is one that can generate a lot of data with a short program.
So, like, it can explain a lot with very little.
Exactly. So it's like elegance in a way.
Elegance, yeah.
Yeah.
Okay, that's a really powerful.
It is, yeah.
And different way to think about information.
It is.
Are there limitations to this approach, though?
There are, yeah. Kolmogorov complexity is fundamentally, it's uncomputable.
Okay.
Although we can get approximations.
Right.
It's also an asymptotic measure, which means that, like, the constant factor involved can sometimes be significant. And while the shortest program is, like, theoretically ideal, finding it isn't always practical.
Right.
And also, its universality kind of depends on the Church-Turing thesis.
Which we might get into later.
We might touch on that.
Okay.
Yeah.
Still, though, this idea that complexity equals information, it's quite compelling.
It is. It's very elegant.
Some even see it as, like, more fundamental than Shannon's entropy.
Right. It kind of gets at something deeper, you know?
Yeah.
The idea that algorithmic complexity could be the foundation for AI and, like, a general theory of knowledge that's very appealing to a lot of people.
It's like a grand unifying theory of thought itself.
Yeah, kind of, yeah.
Oh, okay.
Some even argue that data compression, that's the core principle of how human cognition works.
Oh, wow.
So it's like we're constantly trying to find those shorter programs to explain what we see, what we experience.
That's really interesting.
It is.
Okay, so we have these two major mathematical theories of information.
Right.
Is there a way to bridge them conceptually?
That's a central question in the philosophy of information.
Yeah.
One way to approach it is to
Right.
consider the relationship between information and those fundamental mathematical concepts like sets and numbers.
That's a number.
Yeah, like a lot of the open questions in the philosophy of mathematics, they seem to touch on the very nature of information itself.
Okay. Can you give an example?
Sure. Think about something as basic as tally sticks.
Okay.
Right? They represent the simple form of information measurement through, like, the concatenation of symbols.
Okay.
Right? More marks means more items.
Yeah.
This highlights the idea of extensiveness in information.
Extensiveness of it.
But even here, like a single mark that only carries information because we've agreed it means something.
Right. It has to represent something.
Exactly. And this introduces the role of symbols and like semantic context,
Okay.
even in the simplest forms of information.
So information isn't just about the physical representation,
Right.
but about the meaning
The meaning we attach to it.
that we attach to it.
Exactly.
Okay. Okay. That's interesting.
So consider like early accounting systems, using those clay tokens,
Okay.
different shapes and quantities represented different goods.
Mhm.
So the evolution from just like unordered collections, like sets,
Right.
to ordered collections on strings, like sequences, it shows how the structure of information can convey more complex meanings.
Right.
Sets, multi-sets, and sequences, they each capture different aspects of information.
Okay.
Right? Presence, frequency, and order.
Okay. So like, is it there? How much? And in what order?
Exactly.
Right.
Exactly. And you can even relate these structural properties to like logical concepts
Right.
like contraction, commutativity, associativity.
Right. Right. Those logical rules.
Exactly. Yeah.
Okay.
So systems that treat information like sets, they obey these rules.
Okay.
Right? And by looking at which rules are preserved, which are discarded,
Yeah.
we can understand what kind of information is being represented.
Okay.
So sets, for example, they kind of relate to this naive view of information
Naive. Okay.
where novelty is key.
Right.
Like, is it new?
Is it new information?
Yeah.
Okay.
Multi-sets, where frequency matters.
Hmm.
Those connect to Shannon's information theory.
Okay.
And sequences where order is crucial.
Okay.
Those relate to Kolmogorov complexity.
Okay. So it's like these different ways of thinking about information
Yeah,
map onto different mathematical structures.
exactly.
Okay. That's really cool. What about numbers themselves, though?
Right.
How can we measure the information contained in a number?
So for a philosopher, consider defining a measure of information for a number n
Okay.
by imposing some natural constraints.
Okay. Like what kind of constraints?
So if the information in the product of two numbers is the sum of their individual information, we call that additivity,
Okay.
right? If larger numbers contain more information monotonicity,
Okay.
and if we set a basic unit normalization,
Right.
mathematically, the logarithm is the only function
Oh, wow.
that satisfies those conditions.
It's like it's the perfect fit.
It's a perfect fit, yeah. So this leads us to define the information in n as log base A of n,
Go.
where A gives us our unit, like bits, nats, Hartleys.
Right. Those different units of information.
Exactly.
Okay. So that elegantly ties the measurement of information
Yeah.
to this fundamental mathematical operation.
Yeah.
Okay. And how does this relate to probability within sets of numbers?
Okay, so if we consider a finite set of numbers,
Okay.
the conditional information we gain by identifying a specific element, given that we know the set,
Okay.
that turns out to be equal to the logarithm of the size of the set. And this is also related to the probability of selecting that element randomly. So
Okay.
it all ties together,
Yeah.
And this leads to something called the unification theorem,
Okay.
which connects conditional information and probability within a set, the Hartley function,
Okay.
which measures the information revealed by randomly selecting an element.
Right.
That also aligns with Boltzmann and Shannon entropy under uniform probability distributions.
So it's like it all comes full circle.
It all comes full circle, yeah.
It seems like math provides this powerful framework for unifying these different ideas about information.
It does.
You also mentioned the information efficiency of mathematical functions.
Right.
What did you mean by that?
So we can define the information efficiency of a function as the difference between the information and its input
Okay.
and its output.
Okay.
So addition, for instance, while it loses some information for numbers greater than 1, it still preserves information about the value and the frequency of the units.
Right.
Multiplication, on the other hand, that's largely information conserving.
Oh.
And it connects to prime numbers as like these fundamental building blocks of numerical information, as stated by the fundamental theorem of arithmetic.
Right. So it's like prime numbers are the atoms of numbers.
That's a great way to put it. Yeah.
Okay.
Yeah.
And the irregular distribution of primes and the difficulty of factoring them, these also have implications for information when viewed through a philosophical lens.
Absolutely. The fact that primes are distributed in this seemingly random way and that factoring large numbers is so computationally difficult,
Right.
those raise some really deep questions about the nature of mathematical information
Oh.
and how accessible it is.
Okay.
You know, the difficulty of reversing certain operations,
Right.
like factorization that underpins modern cryptography,
Oh, wow.
you know, highlighting this intricate relationship between information,
Right.
computation, and even security.
Okay. So it's like it's a practical implication
It is, yeah.
of these abstract ideas.
Yeah, very much so.
Okay. That's a great bridge to our next topic.
Mm.
Information and symbolic computation.
Right.
So we've been talking about math on numbers.
Yeah.
But computation, a lot of times, involves manipulating symbols.
Absolutely.
How do these relate for philosopher thinking?